And it goes a little something like this. The first derivative tells us the slope of a graph, yes? Yes, okay. The second derivative, I guess what tells the slope of the first derivative's graph, but that's not important. The second derivative is the change in the first derivative. Okay? Now if you put those two things together to get a visual, if the first derivative is slope, and the second derivative is change in the first derivative, then the second derivative is change in the slope. Hi.
Hi.
Grass. Change in the slope, okay? Second derivative tells us change of the slope of the graph. Okay? Now, let's talk about this then. Say, what's happening if the second derivative is positive? Now, if the second derivative is positive, that means the first derivative is increasing. These little jumps in connection are key to understanding calculus at a deep level. You make little steps of deduction, all right? Second derivative is the change in the first derivative. So if the second derivative is positive, that means the first derivative is changing in a positive way or increasing. If f prime is increasing, then the slopes of f are increasing. All right, now I'm starting to get a feel for it. Now let's draw it. If I had a curve where the slope was here at one point, and then the slopes are increasing, then the next time they're going to be a little steeper, and a little steeper, and a little steeper. So you get a curve. Actually, let's start there. A curve. Linear functions don't have change in slope. They always stay the same slope, right? So the minute you change slope, you'll get a curve. The question then is, how is it curving? Well, this is concave up. Now, concave up is really this graph or any chunk thereof. So if you had this, that's concave up. If you had the whole diff, that's fine, or this, that's fine. Those are all versions or forms of those concave up, because in every one of these cases, if I draw the tangent line, it's increasing in slope, yeah? All right. Would you also notice that tangents lines lie below? If I were to draw any tangent lines lie below concave up curves, and secant lines, if you were to draw a secant line between any 2 points on the curve, secants are above. I should have written out secant so it doesn't get confused with secant, but the secant slope or secant lines are above. All right? Now, if the second derivative is negative, by similar reason, then f prime is changing in a negative way or decreasing. If f prime is the slope of f, then that means the slope of f is decreasing. So if you drew any old slope and then started to decrease it, well, see, that slope was 2 over 1. Then if you decreased it, it might be 1 over 1, or 0, or negative 4, or negative 4. That curve then that is generated by slopes decreasing is called concave down. We then start to get a feel for not just increasing and decreasing, but concavity, or how it's curving as well, any form thereof. You can see that any tangent lines on concave down are above the curve. Secant lines are below. Okay. Again, it doesn't have to have the whole shape of this to have concavity. For example, if I gave you negative e to the x, the graph would look like this. And is that concave up or down? Concave down, yeah. Okay, now, one skill then, you need to be able to take some information about the first and second derivative and sketch what's going on with the graph there, given that information. do one or two together and we'll start to get a feel for this and you'll do the rest on your own. So look at A. I give you that for all real numbers, the first derivative is positive, the second derivative is positive. Now I gave you a little space next to this to interpret this. If the first derivative is positive, that implies the curve is increasing. First derivative positive implies the function is increasing. Second derivative positive means it's concave up. Concave up. The slopes are increasing, so it's caving up, concave up. So if I were to graph something that's increasing concave up, what would that look like? Would it look like this? Okay, it's right on one side, but not right on the other. What's it good on? It's good on the concave up part, the right side, right? I said that wrong. It's cool on the concave part, but is it cool on the increasing part? No, it's decreasing here. So that's not good. I need it to be always increasing concave up. So maybe something like that. Like maybe an e to the x curve. Okay? Try B. Tell me what is, you need to make the connection. What does this tell you? Increasing, decreasing, concave up or down, and then draw. So, did you get decreasing concave up? Does your graph look something like this? Yes, okay. Try the last one, C, and then we'll go on to two regions of behavior. Okay, so what's the behavior for C on all reals? Decreasing concave down, all right? So I need, as I go left to right, the y values need to go down, and the curve needs to curve down, or slopes need to decrease, so boom, like that? Okay, cool. Alrighty then. You'll then start to get into two regions where things kind of switch over here. So for D, for example, we'll do one together, and the other two you'll do. It's going to go decreasing concave up, and then what's the next region of behavior? Increasing concave up. So I'm going to locate 0. Don't worry about the vertical component to this. I don't know vertically what this is. I don't care. Okay, I just care about where it's going to switch off behavior x-wise. That's horizontal. All right, so I need to graph something that's decreasing concave up to 0, and then it goes increasing concave up. So it's decreasing concave up. At 0, then it starts to go increasing concave up. So maybe something like that. Forever. Yeah? Try the next two on your own. We'll go over it together. I'll walk around. If you do that pointer, feel free to pop it open. Say, hey, is this what you have? The second one's kind of funky. Make sure you're on the right track. E, so decreasing concave up, that's cool. Like that, right? And then all of a sudden it turns to, at 0, starts turning increasing concave down. So what does that look like? Yeah, like that. Okay? All right, if that went well, keep going. You're on the right track. By part F. Okay, so decreasing concave down. Decreasing concave down like this, yeah? Increasing concave up like that. That's something what yours looks like? Yes, sir.
So since for both of those, like it goes at zero, it goes straight from decreasing to this look goes straight from decreasing to increasing.
Yeah.
Does it have to have like cusp shape? Like can it not be smooth?
I cannot figure a way out to make it smooth there. So yes, I cannot, unless you have something that I can't see, I believe they will be cusps, yes. Now that actually, you can see a lot of these then are indicate minimum maximum. That's the idea of the first derivative and tomorrow's second derivative test. So we'll go on tomorrow to say what does the second derivative tell us about extrema. There's a whole different test. So you're very insightful, sir. Go to G. It's a 3-region graph. Try graphing by showing what's happening in the 3 regions indicated. And then might as well go on to H after, and then we'll move on to H also, which is going the other direction from the graph to the table. How are we doing, G? Okay. What's special about what's happening at 2? What's going on at 2? What's going on with the graph? Something happened at 2. What? Say again? The concavity change. Thank you. So the concavity change, that is actually a kind of important part of the graph. We'll see that on the back. But if concavity changes, that's called an inflection point. We'll get to that on the back side. If the concavity change in concavity, but not in extrema. And it's an inflection point. Okay, how about this? Did you get a chance to finish H or in 1 more minute? We're cool? Okay, in the first section, up to 0. What's the sign of the first derivative? Positive because the function is increasing. What's the sign of the second derivative in that region? Negative because the curve is concave down. All right, from 0 to 2, that's in here. Oops, it's supposed to be like that. Sign of the first derivative? Negative because the function's decreasing, and concave down, which implies the second derivative is negative, okay? Concave down, the second derivative is negative. After 2, the derivative is negative because the function is decreasing, and the second derivative is Positive because the curve is concave up. Are you with me? All right then. That's graphically starting out. Let's do this numerically here. Now this is usually a multiple choice question on the exam that have really low averages. People just don't think about it in the right way. With the right approach, it's really pretty easy, all right? So I tried to lead you there. A derivative is the rate of change. So the second derivative, you could say it's the concavity of the function. However, you don't always have the graph to look at. So you could also think of the second derivative as the change in the change. The first derivative is change, the second derivative is change in the change. When dealing with a table of values, not like numbers, not signs like above, then use these two big ideas. If the first derivative is positive, the function values are increasing. That's not new. We know that when the derivative is positive, the function is increasing, right? What is new is if the second derivative is positive, then the changes for the first derivative are increasing. So with that in mind, say you have this table here and you have a couple points. F has first and second derivative positive for all real numbers. Given the table, what could you tell me about that next point? What would happen as we get to that third point? Let's start here. If the first derivative is positive, that implies f is increasing. So that right away tells you f at 5 must be greater than 7. Okay, it has to be bigger than the previous y value because it's supposed to be increasing, right? And that one's pretty easy. F double positive means f prime is increasing, which should mean the changes, you can look at it, let's say it this way. It's increasing at an increasing rate. In that case, then you need to look at the changes. The previous change from 1 unit over was a change of 4. If the changes are increasing, then the next change must be greater than 4. Next change, more than 4. So that implies f at 5 must be greater than 11. I have to go up by more than 4 next time, so if I start at 7, go up by more than 4, I have to be more than 11. You with me? Try then a slight change. So what can you tell me? F at 5 must be greater than 7. Why must it be greater than 7? The first derivative is still positive, so it's still increasing. I still have to have that it's greater than 7. What about another fact, though? Less than 11. Because the second derivative is negative, the next change must be decreasing from 4, so it must be less than 11. So I know f at 5. Now you can see that in a multiple choice, they might say, which of these is a possible value for f at 5? And they will give you 6 and 8 and 13 and 15. And you just understand, well, it's got to be here and here. You can rule out choices, a couple choices with the first derivative, and get it down to the final choice with the second. You with me? Okay. All right, then, analytically. We did this graphically, we did this numerically from a table of values. The most common columns, the ones we do most often, are analytically, where we've given an equation and we're taking derivatives and such and working with it. So let's get some practice on that. If I asked you, is this curve concave up or down at x equal 2, you are not to do this visually. It's to be done analytically. The idea is you need to determine if it's concave up or concave down. What do you need? This concave up means the slopes are increasing, right? If something's concave up, then the slopes are increasing, which means the second derivative is positive. So you need the sign of the second derivative at 2? That's really the question. Okay, so surely then we'll need the second derivative. Start with the first derivative, which is 3x squared plus 4x minus 4. Now, in a lot of problems, I pause at the first derivative, find where it's zeros and all that stuff. I don't care. The second derivative is just a way to get to the first derivative is just a way to get to the second derivative. So I'm just going to keep on going to the second derivative, which is 6x plus 4. All right? I then test the sign of the second derivative at 2. They asked for what's the concavity at 2? Is it concave up or down? So that would be something like 12 plus 4 or 16. Now just to find the answer. Okay? Is this concave up or concave down? Concave up. In order to justify that, you'd say this is greater than 0, so f is concave up at x equals 2. Now, there's a huge danger here in AP pre-response questions. You have 3 subjects. You have F, F prime, and F double. And in justifications, people tend to say one when they mean the other. Okay, so let's be clear. The function F is concave up because the second derivative is positive. It's not the second derivative is positive, so the second derivative is concave up. It's not. The function is positive, so the function is concave up. Okay, do you understand? And you have to be very clear with what's causing what to happen. All right? Try that one on your own. I always enjoy giving you the harder of the 2 problems. So, should we look up our notes, or do you? And somebody throws the phone so we don't have to get the notes out. Actually, I love the notes. That's great reference. I cannot for the life of me get junior high kids to use their notes. They don't. They have no idea why you take them. All these equivalences, all these choices to make, and going on to the second derivative, make your life easy. Ask what would be easiest. If you know secant's derivative, then bust out the chain rule. But if you don't remember secant's derivative, and you just put your notes away, foolish, then I guess you should use cosine. Are you doing chain on secant or chain on cosine? Secant, okay. What's the secant of pi over 4? 2 over root 2 or root 2. Either one's fine. Tangent of pi over 4? 1. Okay. So altogether then, the second derivative at pi over 4 is 8. Okay. So our conclusion is that the curve must be, the second derivative is positive, so the curve f is, did I make a mistake? 4? Sorry, 4. Why are you confused? Okay. The second derivative value is 4, which is positive, so f is concave up at pi over 4. Graphically, does that make sense? What does tangent's graph look like? Yes, like that. Has an asymptote at pi over 2, so where we're talking about at pi over 4, does it make sense concave up there? Yeah. Okay. In terms of interpreting slope, we don't do this much, but that second derivative 4, I guess if you were to interpret it, it means the slopes are increasing at 4 units per unit change 1. You don't do that much. All right, last but not least, we talked earlier about a place where the graph changes concave, but is not an extrema. That's called an inflection point. An inflection point is where the second derivative is 0 and changes sign. Not just second derivative equals 0. This is a fight like heck with the BC students. It's not just with the second derivative is 0. Don't just find the second derivative is 0 and circle it. You have to establish that the graph changes sign. So, if you start with the old first derivative in this problem, is, I believe it's the same as the previous function, but we're going to do something different with it. There's the first derivative, 3x squared plus 4x minus 4. Okay, f double is 6x plus 4. Now we want to know where this is 0 and then see if the second derivative changes sign around this. So let's start by finding the 0. This 0 is out at negative 2/3. If I look at x is less than negative 2/3 and x is, let's just do a sign chart, shall we? Now I'm testing the second derivative. Again, there's all these things going on. I have the function, I have the first derivative, I have the second derivative. Be very clear in your mind what you're doing. I'm trying to see if the second derivative changes sign. So I'm sign testing the second derivative. Give me a number below negative 2/3. Any number. Negative 11. All right, whatever. Negative 66 plus 4 is negative. Give me a number above negative 2/3. 0. 0 plus 4 is positive. Last gotcha. This is kind of like a gotcha on the last test. It says find the inflection point, not x, point. Okay, that's coordinates. So you need to say f has an inflection point at negative 2/3, and then you have to find the y. Why did I make this problem so hard? Where do I put negative 2/3? Into the second derivative, the first derivative, or the function? The function. So f at negative 2/3 is, I'll race you. You just do it for me. That's fine. We got negative 8/26 ninths plus 4/9, 8/9 plus 8/3. That's 1. 7, 8 plus 9 is 72. Minus 27, I get something like, what do you got there? 83, 69 minus 8, 61/27. Okay, now that's a point on the original function. I hope I did that right. Is that all the notes on this side? I think so. I just summed it up then, all right? The huge ideas of this were these. If the second derivative is positive, then that implies f prime is increasing. And it also implies that the graph of the original function is concave up, the slopes are increasing. If the second derivative is negative, the derivative is decreasing, which means the slopes are decreasing, and the graph of the original function is concave down. Last but not least, if the second derivative is 0 and the second derivative changes sign, then the original graph has an inflection point. An inflection point at x equals. Now there's actually a whole other use to the second derivative test for extrema, but I just, from experience, there's just no way to do it well in one day. There's just no way. So I will get to that tomorrow. That'll be extra practice tomorrow. And yeah, that's it. Okay. So these are two things. I want to get to any questions you have on homeworks, preferably 45 and 6 if possible. But I also want to make sure you're cool on infinite rectangles. Tomorrow you'll have a quiz. There will be one infinite rectangle problem and some redemption quizzes, questions over the test. I thought about, I guess we'll test it, but whether should redo a question or not redo a question. I'll tell you what, I'm going to throw you a bone here. And I will, if you give it a go tomorrow on a question, and you do worse, which shouldn't happen, I think people all agree. But if for whatever reason you do worse, I'll keep your original score. So you can only do better. Understood?
Yes.
Okay. All right. Questions on set 45, 6? If you have questions on an infinite rectangle, do we still have 45?
Yes.
Okay, if you have a question on an infinite rectangle question, let's go over that one, but I'll take any question. I think there was a legal size one. Let me know if you have question 9. 24. 4. 11.
Oh wait, never mind.
Never mind. Okay, 9, 24, and 4. Let's get those knocked out. It would be great if I could get 45 and 46 today. So we're not so backed up. And then we'll just have 47, 48, and 49. Only have 3 sets tomorrow. That'll be great. 9. 9 is... Okay. So you've got sine from 0 to pi, 4 subintervals. God darn it. Sine 0 to pi, 4 subintervals. Now, this I gotta tell you, I blew it. When I went to plan my first rectangle lesson, I was just thinking you only needed to know left and right, not upper, lower. But looking at AP tests, there is a question or two once in a while on lower and upper, although left and right are far more common. So I'm going to gradually over this week and next week rectify that. Might as well start now. This question was about lower rectangles. So let's talk about what's implied by that. Now, if you didn't do it this way, if you just use left or right, that's my fault because that's what I taught you. But let's start talking about this. 0 to pi, the graph of the sinusoid would be a full wave is 2 pi, so we're looking at a half wave above the axis on 0 to pi, right? All right. Now, if I divide this into 4 subintervals, then surely that means each subinterval is pi over 4 wide. Now, because they are equal bases, this is a case where I can factor out the base. And the common base for all is pi over 4. All right, now let's talk about the lower part of it. That's where the news. Lower means in each subinterval, you choose the smallest y value. So, for example, in this first subinterval, the lowest y value would be f at 0. Okay, in the next subinterval, which is from pi over 4 to pi over 2, you choose the lowest y value, which is, because it's constantly increasing, the lowest would be at pi over 4. In the next subinterval, it's starting to decrease now. And so now we're not going to use the left point anymore. Now we're going to use the lowest point, and it'll be on the right. So it'll be at 3 pi over 4. And in the last subinterval, the lowest point is f at pi. So that your final answer should be pi over 4. F at 0, sine of 0 is 0. What's sine of pi over 4? Root 2 over 2. What's sine of 3 pi over 4? Also root 2 over 2. And f at pi is 0. What's root 2 over 2 plus root 2 over 2? 2 root 2 over 2, or just root 2. So we get something like pi root 2 over 4. Those obviously don't cancel because we're in roots, so that's as good as you're going to get. Does that make sense?
Yeah.
Okay. We'll give you more practice on that, sorry. 24 on this is find the sum of the first 20 terms. Now, let me model. Okay, so if you were a math person, and a person came up to you and asked you this 20 years ago, and you thought, well, I know there's some formulas, but I don't remember them, you could still answer the question. In fact, even a non-mathy person, given enough time, should be able to answer this question. How could a non-mathy person do this? Just brute force. How? Just list them all up and add them up. That's of course, there's a much better way. So let's talk about better way, but without the memorized formula, okay? Wouldn't you agree that the pattern here is plus 3 each time? Okay? So I could continue this until I got to the final term, final few terms. Now, you can see that the first term is -2. Establishing a pattern, the second term, obviously it's 1, but in terms of how I got it, it was -2 plus 3 was. The third one is -2 plus 6, but again, trying to keep it as simple as possible. Wasn't that -2 plus 3 2 times? Yeah. So if the second term was -2 plus 3 once, and the third term is -2 plus 3 twice, and the fourth term is -2 plus 3 3 times, then the 20th term would be -2 plus 3 19 times, which is -2 plus 57, or 55. I could go back a little. What's the one before that? 52, and so on, right? So, all right, that helps me a little because, all right, I know what the first ones look like and the last ones look like. After that, it is a bit of a conceptual thing. Rather than add left to right, we actually add at the extremes. 55 plus 52 adds to 53. In this case, I went up by 3, but this one I went down by 3, so the sum is still going to stay the same, 53. And you went up by 3, down by 3, that would be 53. So you can say that each pair is 53 times how many pairs? How many pairs are there? 10 pairs. There are 20 numbers, so there are 10 pairs. So the sum is 530. Okay. So that's how you would think your way through it without memorized formula. 4. 4 is replaced suppose f is a function that the first derivative at -1 is 0. That should imply horizontal tangent or flat. First derivative is negative. I'm going to do this. Negative when the first derivative is 0. -3 to -1, the first derivative is positive, and from -1 to 2, the negative. It goes negative to positive around that point, yeah? Sketch the graph and indicate a local max or min. Okay, this actually is good. I have something to add on to this that might be fun. If f prime is negative before -1, then what's going on graphically? F is it's decreasing. And then if the derivative is 0, then the graph is flat or horizontal tangent. And then if the derivative is positive, then the graph is increasing. So decreasing, flat, increasing, looks like that. Surely it looks like a min, yeah? Answer me this though. It says from -3 to -1. If it ended at -3, what's there? A min or a max? It's a max, okay? It's greater than the values in its neighborhood. So there's this part of calculus later on about what happens at endpoints. You can see that also they set up to 2 as positive. If they stopped at 2, that also would be a max. It's a local max. Endpoints also are extrema if they chop it and only take a chunk of the graph, then those endpoints can be extrema too. But for now, you can just say f has a min at, do they give you the point or no? At just a -1. I don't really know the y value at x equals -1 because f prime changes negative. Okay. Boom. How about 46 questions? 46 questions on 46. 8 on the back. What else did you say?
Oh, I was confused on 45.
44,
45.
40. Oh, 45?
So like that's 40.
8 on the back and 45.
8 on the back of 45. Aren't we moving on to 46? I'm pretty sure we were. 8 on the back, 8 on the back, 8 on the back. Okay. 8 on the back, I suppose you could do with calculator or now no calculator, but let's say we did it with calculator. You have f prime is 3 sine of 2x over x. How many critical values?
It's x squared.
X squared, thank you. Critical values on the interval 0 to 10. Okay, that, by the way, is an interval, not a point. You with me? Critical values, or critical numbers, are x's in the domain where the derivative is 0 or does not exist. Okay? Now, f prime does not exist at x equal 0. But is that in the domain? Yes, no? No. They give you a parenthesis, non-inclusive the inputs. Okay, 0 is not included. Up to, but not including 0, 0 is out. 0 is not in the domain. Okay? F prime equals 0 at, well, that would be where the numerator is 0, right? Let's bust out those trig skills, shall we? Sine of 2x equals 0. Where is sine then equal to 0? Give me lots of points. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, dot, 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 dot. So if that's what 2x needs to be, then it would be at x of 0, pi over 2, pi, 3 pi over 2, 4 pi over 2, 5 pi over 2, so on. Now I just need to figure out how many of these are in 0 to 10, all right? So this is pi is roughly 3.14, right? So this is 0, Obviously, that's cool, but it's at the edge of the domain, so it's out. That's about 1.5, it's in. That's about 3, it's in. This is about 9 over 2, 4.5, it's in. 4 times 3, 12 over 2, that's roughly 6, it's in. 15 over 2, 7.5, it's in. Gosh, the next one, what would it be? 3 pi. 3 pi 9.42, it's in, right? So 1, 2, 3, 4, 5, 6. I think after that you'll see sometimes it's too big, so it's out. There are 6. You follow? Yes.
On the key on mine, it said for number 11 that, I think it said that 4 was 16.
Oh, that's right. I had an error. Somebody told me you had a third period. 11 should have been 64 for your final answer, not 16. You're right. I had 4 that 4 for 64, not 256. 11 should have been 64. All right. Well, we didn't get to 46, but it's still good. I'm on 45 and 46 today because I don't want 4 sets backed up. So make sure you give me 45 and 46 by the end of the day. What? Everything. Probably not, but it's tonight's homework, so you should be doing it tonight. But honestly, I think we'll probably just get up to 48. 8 is tomorrow. But you will get a new homework tomorrow, so make sure you're keeping caught up.
Thank you.